All right, I think we have quite a bit of people. So welcome everyone. So this is, the next iteration of the ISCA SIGML seminars. And today we're very happy to have Kaizhi Qian to talk about unsupervised speech disentanglement for speech style transfer. And Kaizhi, I think he graduated from UIUC a while ago, right?
Yeah.
And then your advisor was Mark Hasegawa-Johnson, and then now he's a researcher at the MIT-IBM Watson AI Lab. And and so Kaizhi, the floor is yours. Take it away.
Yeah, thanks for the introduction. So let's get started with the presentation. So I'm going to introduce a series of works on unsupervised speech disentanglement for speech style transfer. So first, I will introduce AutoVC, focusing on Tamer style transfer, which is usually called voice conversion in literatures. Then I will introduce speech split, focusing on local prosody style transfer. And finally, I will introduce AutoPST, focusing on global prosody style transfer. So to start with, let me first briefly explain what is speech style transfer. Speech style transfer refers to a set of tasks which, given a source speech and some target domain information, produces a converted speech that resembles the target domain in terms of style, but retains the content of the source speech. Depending on how the domain is defined, the speech style transfer problem can be broken into different subtasks. For example, if the domain corresponds to different speakers, then the task becomes voice conversion. If the domain corresponds to different emotion categories, then the task becomes emotion style transfer. In this talk, we will be focusing on non-parallel style transfer, which assumes no parallel data across the source and target domains are available during training. Before looking into style transfer, let's see what different components does speech contain before trying to convert them. If we represent the full information of speech as a bar, the major components of speech can be represented using the following blocks. The first block is the content block, which can be transcribed to text in most languages. The second block is the Tamer block, which characterizes the speaker's voice. The third block is the pitch block, which characterizes the intonation. And finally, the fourth block is the rhythm block, which characterizes how fast a speaker speaks. Our goal is to disentangle all components in order to perform style transfer on each and a different combination of these components. And we would like to do this step by step because this is a very challenging problem. So we are going to do this, start with the easiest component. And because we have speaker identity label for Tamer, we will disentangle Tamer first. So we proposed AutoVC for disentangling Tamer, which is the first zero-shot non-parallel many-to-many Tamer conversion or voice conversion framework. Before AutoVC was proposed, the existing methods use complex architectures or training schemes, but still don't generate natural sounding results. And they can only convert between scene speakers. On the contrary, AutoVC has a very simple autoencoder architecture, and we can show that autoencoder is all we need to achieve natural sounding speech. AutoVC is also among the very first algorithms that can convert between unseen speakers. I will describe more details in the following slides. So for training, the AutoVC consists of an encoder, a decoder, and a pre-trained speaker encoder, where the encoder has a low dimensional bottleneck as indicated by the gray tip. During training, the encoder takes the input speech and output the content code. The speaker encoder takes the input speech and output the speaker identity label. Here, we assume that the speaker ID contains almost the equivalent information to Tammer because different people have different characteristic voices. Hence, we use the same block pattern as the Tammer component to represent the speaker ID. Finally, the decoder takes the content code and the speaker label to reconstruct the input speech. It is only trained on self-reconstruction loss. And we will show that by carefully tuning the bottleneck, the conversion result will match the distribution of the target speaker uttering the content of the source speech. As I mentioned, AutoVC can perform zero-shot conversion, where either or both input voice and the target voice can be unseen. In order to achieve this, when training AutoVC, we use the fixed speaker encoder pre-trained using thousands of voices. During testing, we can replace the input to the speaker encoder with the seen or unseen voices, thereby achieves zero-shot voice conversion. Now let's go over the principle behind it. The encoder output is constrained by a small bottleneck, as highlighted by the gray tip. That means the encoder cannot pass all the information through. It has to selectively pass information. If the decoder wants to perfectly reconstruct the input, the encoder has to decide what information to discard. In this case, since the Tammer info is fed to the decoder, the best strategy for the encoder is to discard the Tammer info without hurting the reconstruction performance. So the encoder would squeeze out Tammer because this info is already supplied. In this way, AutoVC achieves disentanglement of Tammer. And this is the only feasible solution to achieve perfect reconstruction under the bottleneck constraint. So here are some results. Notice that these results are, we demonstrate here, is from the most challenging cases because the source speech are all unseen in the training set. So for example, let's see this unseen male voice converted to a seen male voice. So this is the source. Can you hear the sound?
Nope. When you share screen, did you remember to click to share your audio?
Yeah, I think I forgot to share the audio. Let me see if I can. Okay.
Please call Stella.
Can you hear it now?
Yep.
So yeah, this is the source voice, and this is this unseen source voice, and this is a seen male voice in the training set.
Ask her to bring these things with her from the store.
And this is the result.
Please call Stella.
And we can also convert this unseen male voice maybe to a unseen male voice. So this is the source.
Please call Stella.
This is the target voice.
Ask her to bring these things with her from the store.
And this is the result.
Please call Stella.
Or maybe convert this to an unseen female voice. So this is the target voice.
Ask her to bring these things with her from the store.
And this is the result.
Please call Stella.
And also we can convert this unseen female voice to some of these seen or unseen voices. For example, first let's listen to the source.
Please call Stella.
And let's convert this to an unseen male voice. So this is the target.
Ask her to bring these things with her from the store.
This is the result.
Please call Stella.
Or maybe convert to this unseen female voice.
Ask her to bring these things with her from the store.
And this is result.
Please call Stella.
And this bar plots show the subjective speech quality mean opinion scores evaluated by human listeners. So as we can hear and see, the AutoVC achieves very good results that outperforms the baselines under all conditions. It is also the first voice conversion framework that achieves zero-shot voice conversion. So after successfully disentangling Tammer, we would like to see how other components can be disentangled. We proposed speech split to convert Tammer, pitch, and the rhythm. If we have labels for the other aspects, we can follow the same scheme as in AutoVC to disentangle each of them. But the question is, do we have labels for the other aspects? For Tammer, we have an easy to obtain label because we assume that the speaker ID contains almost equivalent information to Tammer. That's also why voice conversion is one of the most successful speech disentanglement applications so far. For content, there is text label, but it is very expensive to get for low resource languages. We would like to develop speech disentangling algorithms for all languages instead of the few high resource languages. So we don't want to use text transcriptions. For rhythm, the aligned text transcriptions tells us the length of each syllable. For the same reason above, we would like to avoid using it because it is hard to get for low resource languages. Finally, for the pitch, we have pitch contour. Pitch contour is the pitch frequency as a function of time, but it shows the length of each voiced segments. So it is entangled with the rhythm information, which does not make it a perfect label for pitch. So is it possible to disentangle speech without the text transcriptions? The answer is yes. In particular, we propose speech split, which can decompose speech into content, Tammer, pitch, and rhythm without relying on text transcriptions. It extends AutoVC by introducing 3 encoders with bottleneck. It is among the first algorithm to convert pitch and rhythm without text transcriptions. And I will introduce speech split in more details in the following slides. Speech split consists of 3 encoders and 1 decoder. And the goal of the decoder is to reconstruct speech based on the outputs of the encoders, as well as the speaker identity label. The 3 encoders are called the rhythm encoder, the content encoder, and the pitch encoder. Notice that there is a great tip on each encoder. This is to emphasize that we impose a stringent bottleneck at the output of each encoder so that none of them can pass too much information. As we will show, these bottlenecks are the key to the success of speech split. The 3 encoders are almost the same, except for 2 differences. The first is the input to the rhythm and the content encoder is speech, but the input to the pitch encoder is the pitch contour. Since it contains both pitch and rhythm, we use the pitch block and the rhythm block to denote pitch information. Notice that the rhythm block is missing a corner because pitch contour does not contain all the rhythm information. The second difference among the encoders is that there is a random resampling module before the input to the content encoder and the pitch encoder, but not before the rhythm encoder. The random resampling operation first randomly splits the input signal into segments, and then randomly stretches or squeezes each segment before piecing them together. So we can see that the purpose of this operation is to corrupt time information. And thus, the output signals all have a contaminated rhythm block, while the other information remains intact. You may start to wonder why this structure can achieve the blind decomposition of different speech components. So let me provide an intuitive explanation here. The basic idea is that the encoders need to pass all the blocks to achieve perfect reconstruction, but they cannot pass too many blocks due to the bottlenecks. so they have to do it smartly. If we take a look at all the inputs, we can notice that only the rhythm encoder has access to a complete rhythm block. The other rhythm blocks all have something missing in them. Meanwhile, the other information can be supplied elsewhere. Therefore, the rhythm encoder will only pass the rhythm information if the bottleneck is binding. Similarly, given the fact that the rhythm encoder only passes rhythm block, the content encoder becomes the only encoder that can supply the content block, and the rest of the information can be supplied elsewhere. Therefore, the content encoder will pass only the content information if the bottleneck is binding. Finally, the pitch encoder becomes the only encoder that can supply the pitch information, and thus it will only pass the pitch block if the bottleneck is binding. In summary, given the appropriate bottleneck constraints, this arrangement is the only way to achieve perfect reconstruction, hence forcing the disentanglement of all these blocks. To evaluate if speech split really works as expected, we performed several experiments. The first one is the aspect-specific conversion. And here is our demo webpage. So you can find an animated illustration of the mechanism of speech split on the top. Speech split is among the very first unsupervised algorithms that can convert not only timbre, but also pitch and rhythm respectively. So let's look at an example here. Here is the source speech.
5 thick slabs of blue cheese.
This is a male voice at a slow pace and has a steady tone in the last word cheese. And here is the target speech.
5 thick slabs of blue cheese.
We can hear it utters the same content, but is totally different in all other aspects. It has a female voice at a faster pace and has a dropping tone in the last word cheese. Now, if I check the rhythm aspect to be converted, we can see that the length of the spectrogram is shortened and aligns well with the target speech. If I play it,
5 thick slabs of blue cheese.
we can hear that everything else remains the same as the source speech except for the speech rate. Similarly, if I only convert pitch,
Five thick slabs of blue cheese.
the last word cheese is changed to a dropping tone, but everything else is the same as the source. Finally, if I check all three aspects, the converted speech will look and sound very similar to the target speech.
5 thick slabs of blue cheese. 5 thick slabs of blue cheese.
So it is impressive that this is done without relying on any text transcription labels. Now let's go back to the slides. We also performed a subjective evaluation on Amazon Mechanical Turk, where the subjects are asked whether each of the aspects is more similar to the source or to the target. These bar plots show the conversion rates, which is the percentage of the responses that choose the target. As can be seen, all the conversion have high conversion rates for the aspects that are converted and low for the rest. For example, if we only convert the rhythm aspect has a high conversion rate. For the second experiment, we would like to see what happens if we set each of the 4 aspects to zeros? Here is the original speech. And here is speech with 1 aspect removed. In particular, if the content is removed, the output becomes a set of slots with no informative spectral shape, and the slots are perfectly aligned with the original speech. This suggests that a speech split may perform a fill-in-the-blank operation, where the rhythm encoder provides some empty blanks and the content encoder provides the content to fill in the blanks. This hypothesis can also explain why the speech becomes empty when the rhythm is removed. This is because there are no blanks to fill, even though the other information is available. Next, when the pitch is removed, the output pitch becomes constant, as indicated by the harmonics. When the timbre is removed, the formants will shift a little, indicating the voice has changed. In summary, speech disentanglement has been challenging without text transcriptions. However, with a set of carefully designed bottlenecks, speech split can achieve unsupervised speech decomposition and, therefore, can perform aspect-specific conversions. Speech split has made a sizable step towards disentangling rhythm in an unsupervised manner, but it requires ground truth rhythm from the target speaker in order to do the conversion. If there is a significant content mismatch between the source utterance and the target utterance during conversion, the prosody conversion may fail. In addition, partly due to the above reason, speech split only converts fine-grained local prosody. And our goal is to find a way to convert global prosody without using utterances with the same content. So we propose AutoPST, which is among the first algorithms that it can successfully convert rhythm without parallel data or text transcriptions. Before I describe how AutoPST achieves this, I would like to take a moment to explain what we actually mean by rhythm information. Suppose a speaker wants to utter a word, say cat. Notice the cat consists of 3 phones, forming a phone sequence of length 3. We refer to such phone sequence information as the content information. Now, let me use blocks of different shades to represent a speech frame uttering each of the 3 phones respectively. If a slow speaker were to utter the word, he or she would produce a frame sequence like this, where each phone is repeated for many frames. If a fast speaker were to utter the word, each phone is repeated for fewer times. Such information about how each phone is repeated across frames is what we refer to as rhythm information. It characterizes the speech rate, pause, and other rhythm patterns of a speaker. Under this perspective, the goal of disentangling rhythm translates to retaining the phone sequence information while obscuring the repetition information. To achieve this goal, AutoPST adopts the following framework. Similar to the AutoVC structure, it contains an encoder, which encodes the input speech feature into a hidden representation, and then a decoder, which tries to reconstruct the input speech. The major difference from AutoVC is that AutoPST contains a 3rd module called the Resampling module, which attempts to scramble the rhythm information by temporally resampling the hidden representation. In this way, the decoder would have a hard time guessing what was the repetition of each phone before the resampling module. So the next question is how to set a resampling algorithm so that it can effectively obscure the rhythm information. To answer this question, let's revisit the cat example. If we observe two utterances carefully, we can see that the phones are not stretched or squeezed uniformly. In fact, it has long been observed that given speech rate changes, the vowel lengths tend to change much more than the consonants do. In this cat example, the repetition of the vowel a changes very significantly, but the other two phones barely change. This implies that the steady segments in speech, like the a segment in our example, would have a larger elasticity. Therefore, in order to truly confuse the decoder, the resampling module needs to mimic this behavior. Motivated by this, AutoPST introduces a similarity-based downsampling algorithm that consists of 3 steps. First, we need to come up with a measure that gauges the content similarity between any 2 frames. In other words, ideally, frames with a similar phonetic content should have a high similarity, while frames with a different phonetic content should have a low similarity. There are many ways to measure this. In our implementation, we adopt a measure proposed by Bati, which has been successfully applied to unsupervised speech segmentation. With this similarity measure, the next step is to go through the speech frames one by one and draw a segment boundary if the similarity between the next frame and the previous frame drops below a threshold tau, as denoted by the red bars on the slide. After the segmentation is complete, the final step is to collapse each segment into one representation by mean pooling. As can be seen, the downsampling algorithm ensures that the steady segments get compressed the most. As you may have noticed, the segmentation threshold tau plays an important role here. If the threshold is high, namely close to 1, there will be many segment boundaries, and the downsampled sequence would be long. If the threshold is low, there would be fewer segment boundaries, and the downsampled sequence would be short. In order to scramble the rhythm information even more, we introduce a random thresholding procedure, where at each frame, a random threshold is drawn. As a result, the downsampled sequence would have some segments that are more compressed than the other, making it even harder to guess the original repetition information. So far, I have only talked about downsampling and the threshold tau being smaller than 1. In fact, this procedure can be extrapolated to upsampling with the threshold tau going above 1. The generalized procedure becomes as follows. We will go through the frame one by one. If the random threshold is below 1, we perform the aforementioned downsampling scheme. If it is larger than 1, we do 2 things. First, we immediately add a segment boundary. Second, if the similarity of the next frame and the previous frame is high enough, we insert yet another segment by copying the previous code. After this segmentation process is done, we follow the same main pooling procedure to get the resampled result. As can be seen, because of the insertion of an additional segment, some parts of the sequence get upsampled, while others get downsampled. Nevertheless, in both the upsampling and the downsampling cases, our similarity-based algorithm would ensure that the steady segments get stretched or compressed the most significantly. That's all for the resampling algorithm, but the resampling module alone is still insufficient to remove rhythm information. This is because in practice, we find that the encoder and the decoder would always try to figure out alternative ways to communicate rhythm information. In order to break such collusion, we introduced a two-stage training scheme as follows. In stage 1, called Synchronous Training, we add a realign module that restores the repetition information so that the encoder and decoder would not find it necessary to collude on the rhythm information. After convergence, we switch to the second stage called asynchronous, where we remove the realign module and fix the encoder. In this way, even though the two players would have the incentive to collude, they are not able to because one of the players is fixed. We perform a set of experiments to evaluate AutoPST's ability to disentangle rhythm, and here are some demos. So let's first see a slow to fast conversion. Here is the source speech,
5 thick slabs of blue cheese.
which is quite slow. And this is the target speaker's voice, target speaker utterance,
The rainbow is a division of white light into many beautiful colors.
which is pretty fast. And we're going to compare three algorithms. First is AutoVC, which we already know would not convert rhythm. And then it's the random resampling, abbreviated as RR, which is similar to our AutoPST algorithm, except that the resampling is not based on similarity. And then finally, our proposed AutoPST algorithm. So first is the AutoVC result,
5 thick slabs of blue cheese.
which is as slow as the source speech. And here is the random resampling result,
5 thick slabs of blue cheese.
which is slightly faster, but still slow. And then finally, the AutoPST result,
5 thick slabs of blue cheese.
which is almost as fast as the target speaker. And then let's switch to a fast to slow conversion. So here is the source speech,
5 thick slabs of blue cheese.
which is fast,
The rainbow is a division of white light into many beautiful colors.
which is slow. And then here is the AutoVC result,
5 thick slabs of blue cheese.
which is undesirably fast,
5 thick slabs of blue cheese.
which is slightly slower. And this is the AutoPST result,
5 thick slabs of blue cheese.
which is almost as slow as the target speaker. So we have seen during the demo that AutoPST has been successfully converting the rhythm. And we also perform the objective measure. We picked some utterances in a test set that are uttered by both fast and slow speakers. For each fast to slow pair, we measure the duration of the fast to slow conversion and the slow to fast conversion, and compute their relative differences called RDD. The intuition is that if the rhythm is converted, then the fast to slow conversion should be longer in duration than the slow to fast conversion. So RDD should be positive. If rhythm is not converted, RDD would stay negative. Here is the box plot of the RDDs across all the test parallel speech pairs. As can be seen, only AutoPST has largely positive RDDs, and the RDDs of the other two baselines are negative. In other words, only AutoPST can significantly change the speech rate to match the target speaker. We also performed a subjective evaluation where the subjects are asked to assign a score of 1 to 5 on the similarity to the target speaker in terms of each of the 3 aspects, namely the tenor, prosody, and the overall. The results show that auto-PST conversion has the highest subjective similarity in all 3 aspects, particularly in the prosody aspect. So far, we have only verified that auto-PST can change the overall speech rate, but the rhythm information is much richer than just the speech rate. We would therefore like to know if auto-PST can capture more fine-grained rhythm patterns. To test this, we artificially create some abnormal rhythm patterns and see if auto-PST can correct it. Specifically, here is the original normal speech.
One showing mainly red and yellow.
We can hear that the last word is yellow. Now we create an abnormal rhythm pattern by stretching the word yellow, like this.
One showing mainly red and yellow.
We then use different algorithms to reconstruct the input speech. If the rhythm disentanglement is sufficient, such an abnormal rhythm pattern should not leak into the hidden representation and should not appear in the reconstructed results. Here is the result of the random resampling baseline.
One showing mainly red and yellow.
As we can hear, it does try to fix the overall speech rate by squeezing the utterance, but it is unable to reduce the duration of the yellow more than the other words. And here is the auto-PST result.
One showing mainly red and yellow.
The abnormality is greatly alleviated, which verifies that auto-PST can disentangle rhythm information beyond just the overall speech rate. To sum up, we introduce auto-PST, a speech style transfer algorithm that can convert rhythm. To achieve this, auto-PST adopts a similarity-based resampling module to scramble the repetition information and a 2-stage training scheme to prevent the collusion between the encoder and the decoder. Our experiments show that auto-PST is effective in disentangling rhythm, including the overall speech rate and the more fine-grained rhythm patterns. In summary, we have proposed 3 works in unsupervised speech disentanglement for style transfer, namely AutoVC, which is the first zero-shot non-parallel many-to-many camera conversion or voice conversion framework. And next, we introduced Speech Split, the first speech style transfer framework that can convert pitch and rhythm without text transcriptions. And finally, AutoPST, which is also the first framework that can successfully convert rhythm without parallel data or text transcriptions. And I will end my presentation here. If you would like to find more about our work, please visit our demo webpage and read our paper. Thank you very much for your attention.
Thank you so much for the great talk. I'm sure people are excited and wanted to ask questions. Yeah, so if anyone has questions, feel free to unmute yourself.
Yeah, I think I've seen 2 questions in a chat. So the first question is, can this convert speech to singing voice? We haven't tried that, but ideally, you can use this framework on singing voice and see how it works. And another person says, yeah, I think that person's referring to some of the demos are losing quality. Probably the AutoPST demos, because we use a very, very narrow bottleneck that has some kind of content loss. because there's always a compromise between disentanglement and content loss. It is very difficult to achieve a good balance between these two aspects. And it's actually one of our future directions to address this problem. And the next question is, did you try to do any correlation analysis of the encoder outputs to verify perfect disentanglement? So what kind of a correlation analysis do you mean? For example, in AutoVC, we did a speaker classification on the encoder outputs, and verify that the speaker classification accuracy of the encoder outputs is 14%, which means there's still some speaker content in the content embedding, content representations, but it is low enough for the decoder to ignore it and perform the Tamer conversion. And what definition of disentanglement have you adopted? So can you be specific about what do you mean by definition of a disentanglement?
I'm curious what you mean when you use the word disentanglement.
It means when we decompose the representations into different subparts, each part only contains the specific information we want. For example, the content code only contains the content information, the rhythm code only contains the rhythm information, and the pitch code only contains the pitch information.
Is that it? There's no other definition. There's just that the representation contains the information that you want it to.
Yeah.
Okay.
Yeah. That's it. And can this be used for native language identification? So how would you formulate this native language identification problem?
No, foreign accent recognition, sir. It is foreign accent recognition.
Foreign accent recognition. Recognition.
Yes, foreign accent, native accent and foreign accent.
I see.
Second language.
Yeah. I kind of know what you are referring to. So all of these frameworks may be useful for foreign accent conversion, but for recognition, that there may be better ways to do it.
Okay. Deviations, identifying the deviation in pronunciation, or deviations in pronunciation. Estimating which native speaker will have certain characteristics of a second language, English as a second language. So whether different countries, speakers from different countries, they will have traits, these common traits, particular traits, native traits.
Yeah.
They can be they can be this thing they can be made into some tables, particular words, keywords, some keywords, how different people pronounce.
I see. Yeah, I think based on what you're describing, there must be other ways of tackling this problem.
Yes. Yeah. Okay. Thank you.
No problem.
I've got my hand up, but I guess nobody's looking at the pictures. Kaizhi, that was amazing. I'm really rather impressed by all your demos and the very clean principles that you're sort of been pursuing. But my question is really about the term rhythm. I'm not used to the term rhythm being used in this way. Rhythm implies repetitive behavior, and you know, different languages have different rhythmic structures, and you know, it's to do with the patterns in the timing, which are repetitive, not just the timing. So you seem to be talking about timing in general, rather than rhythm in particular. And I'm not sure that's a very helpful thing. I think you might want to think a bit more carefully about your terminology there. And the other thing occurs to me that in relation to timing, in many languages, phones are distinguished by timing, not just by their spectral content. So I'm just wondering whether that's something else maybe you just want to think about. I mean, it is well known, for example, that the final consonant distinction between a strong and a weak consonant, the information is mostly in the duration of the vowel. And I'm just wondering whether you're sort of missing a trick there by not appreciating that there are these key timing differences which relate to content. And by calling it all rhythm, I think that's just sort of a dangerous recipe for mixing things up, when, as I understand your architecture, the whole point is to keep it clean and nicely separated. So that's just my thoughts.
Yeah. I think you're right. That's why we specifically say that in our work, we define the rhythm to be the timing that you just mentioned. And since this is also a preliminary work, so we didn't dive too deep into all these details, but we are definitely making other efforts to improve these details, also make distinctions between these terminologies in the future.
Right. So just to be absolutely clear, timing is a very general word. Rhythm means something quite particular. You're using it to mean just general timing.
Yeah, that's really helpful. Thanks.
So do you need to manipulate this model architecture to make it successfully reconstruct the original feature, because you have this kind of bottleneck constraint?
Yeah, so these models, they take a little bit tuning. So the bottleneck dimensions needs to be tuned to achieve a sweet spot. Yeah, that's basically the manipulations.
Thanks.
Maybe it's a good time to jump in here. So you literally just manipulate the dimension of the hidden vectors, like nothing else? Because I feel like the architecture before that vector, for example, how deep it is and how many parameters there are, might also affect the things that might be in that vector. Yeah,
that's true. But in that case, we will have too many variables to tune. So for simplicity, so even though we only have a few parameters to tune, the amount of experiments is still large. So we only tune the dimension, mainly the time and the frequency dimensions of the hidden representations to tune the bottleneck.
So thank you for this nice presentation. My main question is about evaluation. Of course, you had question about content with it's very difficult to really think about disentanglement of the content with prosody, because with tonal languages or whatever, you have always a contribution of prosody in the content. But I think the serious problems are coming just from the evaluation framework. If you just use MOS as a way to prove that you are doing the right way, I think it's really it's too poor, in my opinion, to do the things properly, because it's just involving a global judgment. I think we need to work out the evaluation procedure to have a more clear, even in the evaluation, a more clear separation, disentanglement, in fact, on which criteria the listeners are using for performing judgments. So what is your opinion about, because, you know, just doing MOS for trying to hierarchize, in fact, contribution could be misleading.
Yeah, thanks for the suggestion. And yeah, actually, so in the paper, besides the final loss, during the human subjective evaluation, we specifically give instructions to the listeners and give them examples on what is, for example, what is rhythm, what is pitch, and what is speaker identity, and let them rate each of these aspects respectively. So even though we did not include too many objective evaluations in our paper, but during the subjective evaluation, we give this more detailed instruction to the human evaluators. So this this is definitely not enough and rigorous, but this definitely improve the evaluation metrics of the whole work. And I think there must be other ways of formally or rigorously verifying both the disentanglement and the disentangled quality. And we will, yeah, and we will definitely work on that in our future work.
I think it's a general challenge of this community of speech synthesis or voice conversion is really to accompany this effort of modeling with improvement also on the evaluation methodology. We cannot stay with this MOS scores, which are just very difficult for speakers for listeners to.
Right. Yeah.
To be consistent. It's very challenging. Yeah. So thank you.
Yeah, no problem. Thanks.
So I have to agree with that. I think there perhaps is some space to develop some kind of an informational theoretic type measure, especially if we want to claim something like disentanglement. What is disentanglement? And if there's a definition of it, if you start with a definition of disentanglement, then you can move towards how do you evaluate that? How do you measure this separation of information? And it might not be as rigorous as factorization or segmentation, but it could still be approximated.
Yeah, thanks for the suggestion.
All right, any more questions?
So what next?
What next?
What is next?
Yeah, well, the next speaker, well, on the list.
No, what is your next challenge?
Oh, his next challenge. Okay, go ahead. Yeah.
Go ahead.
I think the next, the next in general, in terms of application, the next challenge would be the accent disentanglement. So just going into more details of the disentanglement instead of just disentangling the voice as a unity. Just break it into more pieces so that we can get more fine-grained control of the conversion.
But I have to add, this becomes very circular because accent will involve many of the things that you're trying to disentangle.
Yeah, that's why it's because these aspects are all entangled together. That's why this problem has been very challenging, and we're finally going to apply some of these techniques to lower source languages. So I think, yeah, exploring these disentangling algorithms should be helpful.
It's connected with the question asked by Radha Krishna. Is in fact what makes the speaker identity is somehow the way you process certain content. Could be markers on specific words or specific rhythmical units or whatever. So as soon as you are dealing with accents and so on, you are dealing with something which is not global anymore, which is perhaps spatiotemporal shapes, which are specific markers of identity or accentual variations. So you need to work on the spatiotemporal arrangement of this the auto encoders should be how to say, aware that it's a sequence and should be manipulating the structures. No, what do you think?
Yeah, I agree. I think we're mostly, I think we're in the direction mostly aligns with what you just described, and also and you can see that in this series of work, especially in the first work, actually the speaker identity is treated as a unity. We don't separate any details, any local things from the speaker identity, and we're just treating it as a global feature characteristics. But in the future work, we're going to focusing on more on local features. Yeah, thanks.
It's so somehow it's like images. You need to be able to decompose, in fact, images into small descriptors which have an extent on parts of the image, in order to be afterwards able to decompose and recompose differently the images. But the how to say, the coins, what is exchanged as basic elements, the atoms, in fact, of voices, which you can identify and then recompose differently according to your application. I think that's the ultimate goal. But my guess is that these coins, these atoms, are spatiotemporal. It's not only a decomposition of vectors, of embeddings, and so on. It's something which is more like dynamical patterns, which are overlapping on space and time. So
yeah, based on the nature of speech, these things are highly entangled.
Yeah.
So we'll see. We don't know how this series of work will go, but we'll try.
And so what do you think about these variational autoencoders operating on sequences? So what sort of technology will be able to answer your questions?
I know these models are used in the early stage of voice conversion. A lot of work used them for voice conversion, and I think they do work well because they have a very nice characteristics of building a stringent bottleneck without any empirical tuning. However, because of the variational variational assumption, there is an upper bound on how the output distribution can match the input. So there's always a gap. So they call this the over smoothing problem. In speech applications where the consumers are usually human listeners, they want the speech output quality to be really, really high. So for VAEs, ideally in theory they work really, they should work really well, but in practice the output quality is a little bit low. So that's the reason why we didn't use that, and people are gradually not using it in speech applications.
Thank you.
Do we have more questions? Well, if not, we can wrap up. Thank you so much, and thanks so much for the lively discussion. Yeah, and right, so we'll see you in probably another 2 weeks, and then we'll have a different topic. And yeah, so hopefully everybody can also join. Thanks again, everyone. I'll see you in 2 weeks.